Welcome to Fundamentals of Computers. In this session, we will talk of CPU operations and we will see how the instructions are linked with the CPU operations. The objectives of this session are to understand the CPU operations better, and we will have a look at specific CPU operation groups within which the operations fall. Then we will have a look at the relationship between the operations and instructions. Finally, we will see how an instruction gets executed, and based upon that, how a specific operation is performed in the computer. As a quick reminder, the computer components are CPU, RAM, and the storage. Out of these components, we had seen the internals of the CPU in the previous session. So in this session, we will have a quick look at what instruction types exist in a general purpose computer. So let's have a look at the CPU operations and the groupings of the CPU operations. There are two types of operations that the computer generally performs. There are more than two types, but a broad categorization is to divide the operations into two types. One are the hardwired operations that get performed continuously without requiring an instruction. These operations get performed on the clock ticks. Most of the time, for every clock tick, one operation gets performed, but it can be a few clock ticks before that type of next operation is performed. The key here is that you don't need an instruction for these operations to be performed. The examples of these operations are incrementation of a program counter PC. Instruction pointer gets incremented at every clock tick. So that happens automatically. No instruction, no specific instruction is required for the IP to increment to the next address. Similarly, RAM address of the instruction, that instruction needs to be fetched into, there is another type of register called IR or instruction register. Copying of the instruction from RAM takes place automatically. Similarly, the instruction residing in the IR or instruction register needs to be decoded so that the computer can understand what operation this instruction is about. Okay, and this is done automatically. There are more examples of hardwired operations. Bulk of these operations are part of the control unit of the CPU. As far as our discussion is concerned, we are talking of software programming. So for the rest of this session, as well as for the subsequent sessions, we are not concerned with this kind of. The second type of CPU operations are the operations where an instruction is needed for that operation to be performed. So for this type of instructions, this type of operations, there are few things that we need to know. First, the operations that a CPU can perform, it depends on the type of CPU. Very well known and commonly known types are x86 based CPUs, ARM based processor, and MIPS based processors. These are three different types of processors. So each type of the processor will have different type of instructions within them. Okay, so what instructions exist in a specific processor? You first need to know the type of the processor, and that will define what instructions are there in the CPU. So all the x86 based processors will generally have similar kind of instructions, and that is defined by the x86 instruction set architecture. When I am saying instructions, that also maps onto the operations. So these are the sets that are defined. Now, why do we define these sets? Why can't we make any operations and instructions, whatever we want to have in our computers? It's because of intercompatibility. So a program that is written for an x86 based CPU or processor can run on another x86 based processor. But the same program cannot, without modifications, run on an ARM based processor or a MIPS based processor. The minor variation between x86 processors, for example, comes based on who has manufactured that specific processor. So for example, the x86 based processors are manufactured by two well-known companies, Intel and AMD. There can be minor differences between a processor. There can be some special, the main instruction set architecture will be common, but there can be some special instructions that Intel decides to add into its processor. And similarly, AMD can decide to add into their specific processor. They have to meet the standard, but on top of that, they can add some special operations. So the two processors created by Intel can also differ from one another because of these special instructions, but those variations will be very minor, one or two instructions, no more than that. Similarly, an x86 based processor designed by Intel and AMD can also have some minor differences based upon the special instructions. Similarly, ARM based processors are created by Apple, Samsung, and Cavium as an example. Irrespective of the type and the manufacturer, the operations can be divided into some larger groups. So let's have a look at the operation groups. We can divide the operations or instructions into four groups. The first group is arithmetic and logic operations. This contains the operations of add, subtract, multiply, divide. The logical operations of AND, or maybe exclusive OR. Similarly, there are some operations that are called shift operations. So shift left, shift right, and so on. And then negation operation, comparison operation, possible, and floating point operations. So these are the operations that are performed by the arithmetic and logic unit. These are the operations that exist in the ALU part of the CPU. The next set. So why exactly do we need? So once again, an add operation on an x86 computer will be performed the exact, let's say an add operation exists for 16 bits in an x86 based computers, but an add operation does not exist for 16 bits numbers in a MIPS and ARM computer. That is very much so. Exact operation within the specific processor will still vary, but more or less there will be one or two variants of add operation in each processor type. The second group of operations is data handling and memory operations. For example, load an immediate value or load a value from RAM into the register and store a value from a register into the RAM. So these operations are used to interact between the CPU and the RAM, specifically with reference to data. Then we have flow control instructions. These instructions help us. We mentioned before that IP address gets incremented automatically. So if we want to change the next instruction that we want to execute, we can use the jump or branch instructions. They can help us for moving from one specific address to a different address that is not the next address in the sequence. So let's say I have executed instruction 1, 2, 3, and then I want to execute instruction 10. By default, the CPU will execute instruction 4 after the third instruction, but using a branch instruction, I can make the CPU execute instruction number 10 instead of instruction number 4. So these are the instructions that change the control of the programs. So they are called flow control operations or instructions. And finally, software and hardware interrupts. These are complex operations, and we will discuss them once we look at the operating system and what is the role of the operating system in a computer. But this is the four type of operations. Now, to look at the specific purpose of each of these operation groups or operations, we need to understand the flow of the program, how the program is written and how the program is created. And I will dedicate the next session for this particular purpose. As far as the existing session is concerned, I have given a brief introduction of each of these groups. So we will stick to this basic introduction. Now we are going to have a look at how a specific operation gets executed in the general purpose computer. This information will be used in the next session, and then we will look at how the programs are created. So so far I have been using the word operation and instruction interchangeably, but now let's have a view of what is the difference between a CPU operation and a CPU instruction. Okay, so for every CPU operation, an operation that exists in the CPU and that is based on the instruction, there exists an instruction. Okay, so what is the difference between an operation and an instruction? Operation is an electronics hardware that is part of the CPU. The instruction is a combination of bits. Okay, so it's a 0-1 value, and therefore it's a software. Each bit in the instruction has a specific meaning, and that defines what this instruction can do. And these instructions are defined in the instruction set architecture. So there is an x86 instruction set architecture, there is an ARM instruction set architecture, there is a MIPS instruction set architecture, and so on. So an instruction completely defines the corresponding operation. Execution of the instruction results in CPU performing that specific operation. Okay, so let's have a look at the CPU instructions. This is the instruction is coming from the MIPS instruction set architecture. Okay, and this is an R-type instruction. What does that mean? I will, for the time being, skip. We will see that in a while. So every bit in this instruction has some meaning, and that meaning is predefined when the processor is designed. So for example, these first 6 bits, they are known as op code or operation code. The last 6 bits represent a function. Okay, this is for R-type instructions, not for there are 2 types of instruction, R-type and I-type. So we are just talking of R-type instructions. This is the function that needs to be performed. This part specifies what operation needs to be performed. And for R-type instructions, that operation's name is known as function. Okay. What this instruction is saying, this instruction once again has these 5 bits ignored. We can discard these 5, we can discard these 6. This one is the op code or function for the function add. Okay, this is number 7, so it corresponds to register R7. This is number 6, so this corresponds to register R6, and this is number 5, which corresponds to register R5. So this instruction is saying add the contents that are stored in register 7 into the contents of register 6, and the result should go into register 5. So what does this mean? It is asking the CPU to perform an operation like this. This is our ALU. ALU has all different circuits in it. One of the electronic circuit is add circuit. So this instruction is asking the computer to activate this add circuit, connect register 7 to the add circuit and register 6 to the add circuit, and then once the addition operation is performed, store the result in register 5. Okay, so you see how the complete operation that needs to be performed is defined by this specific instruction. How does this instruction get executed? Okay, what I'm going to present is a very simplified view of how the instructions get executed. It ignores a lot of CPU optimizations, and it ignores the differences between different CPUs. Different CPUs execute the instructions slightly differently. There are different steps that are involved, but there are some basic steps that are almost performed in all of the CPUs. So we will just talk of those basic steps for the better understanding of writing the programs. Okay, so some relevant details are skipped. They will get covered in the subsequent sections. The instructions reside in the RAM. Okay, they are copied into the RAM. So how are they copied into the RAM? This is the detail that I am skipping for the time being. Each RAM location has an address. So this RAM location has a specific address. The next location has another address. This empty RAM location that is shown as empty also has an address. So you can say that the address of this location is 0. This location has an address of 1. This location has an address of 2, just like the addresses of our homes. Same is the case here. There is a home address. So address of this home or this block is 0, and inside we can have any contents, and those any come from whoever has written those instructions. These instructions are prefetched into the cache. The cache does not have its own addresses. The addresses of the RAM are valid for the cache as well. Okay, so the programs that we write, they only refer to the addresses of the RAM. Automatically, those addresses are converted into cache locations, and the transformation is done by the CPU on its own, an operation that does not need an instruction. We call this process prefetching, and it's mainly to increase the speed of execution of the instructions. We have a specific address in the instruction pointer. Whatever is the address in the instruction pointer, the instruction from that address will be brought into IR register. An address exists in the instruction pointer. The instruction stored against that address is brought into the IR register. This process is called fetch. After this, the IP address is incremented to point to the next instruction. This happens automatically. Okay, so what does this instruction mean? This process, to understand what does instruction mean, we decode the instruction. So this process is known as decode. So suppose this is the same instruction that I showed a while ago. Okay, for the MIPS processor. So this is now residing in the IR. So the decoder of the CPU will come in and try to understand what this instruction is. So it will see these bits. From here, it will conclude that it is an R type instruction. Then it will look at this portion and it will decide that, okay, this is an add operation. So add circuit needs to be turned on. Then it ignores this portion, and then it sees, okay, this is register number 7. This is register number 6, and this is register number 5. So on the input side, connect register 7 and 6. On the output side of the add circuit, connect register 5. Okay, and then on the next clock tick, this instruction will get executed. The next step is execute, where the add operation gets performed. The value of R7 gets added into the value of R6, and the result is stored in R5. All of this happening on a clock tick. This is very important. This is the event on which the computer is responding. So this process will continue to be repeated if nothing else happens. So the next instruction will be fetched from the new address in the instruction pointer, which has now become B. So from B, this instruction will be brought in, and it will continue. The next instruction brought in will be from address C, the next one will be from D, next one will be from E, and this same operation will continue unless we change the instruction pointer to a different address. And this is very, very important operation, changing the address of the instruction pointer. Okay, so these were the instructions. Now you see that the instructions appear as a sequence. Okay, all of them were just a sequence. So how do we know that which instructions to execute in order for a specific task to be performed? For example, if I want to move the mouse on my screen, what should be the sequence of instructions? Which instructions and how to arrange them so that this task gets performed? Okay. Similarly, if I want to open a new program, let's say I want to click on the icon for the word processor so that it can appear on my screen, what sequence of instructions should I write so that this operation gets performed? Okay, we call them programs. We write in a high-level language, and then a compiler converts those programs into the machine-readable instructions. This is something that we will see in the next session, the computer instructions and the computer software applications. Over there, we will also see the purpose of some of the instructions that we saw. We saw the groups, but we did not see the purpose of each group. So in the next session, we are going to have a look at the purpose of each instruction group. That brings us to end of our existing session. Thank you very much for your support and for your time.